Okay, let's talk about the material from lecture 13. This is material on what's called the binomial distribution. I have to stop and say, as usual, that watching videos is not a substitute for reading the book or notes. Okay. We want to define a binomial experiment. Binomial experiment. And a binomial experiment is an experiment. Essentially, the idea is it's an experiment made up of little experiments, and each of those little experiments consists of the same thing being tried over and over and over again. Right? Like flipping a coin, flipping it once, flipping it again, flipping it again, flipping it again, under as near as can be contrived to identical circumstances. Well, rolling two dice. You could roll the dice, roll them on the same surface, same dice on the same surface, roll them again, and so on. And you want to, a binomial experiment is going to be made up of repeated trials with certain characteristics, which we'll get to in a second, but repeated trials that are performed as nearly as possible under identical circumstances. Those trials, right, so you're going to have some rules here. You have to have a fixed number of trials. Right, that number is always called n, and those trials are often called Bernoulli trials, after Jacob Bernoulli, who first investigated this stuff systematically. Well, the trials need to be independent. Right? Like flipping a coin, what comes up the first time doesn't affect the probability that you get heads or tails the second time, and so on. Right? The trials have to be independent. It has to be the case that the only possible outcomes on any one trial are success, which usually is denoted by a capital S, and failure. And they could be called other things, but as long as there are just two of them, you can call one success and the other one failure, and it'd be just fine. Right? And finally, the probability of success has to be the same on each trial. So when you're trying to decide whether some experiment that's been described is a binomial experiment, you want to say, is there a fixed number of trials? Are the trials independent? Are the only possible outcomes on any trial success and failure, or could they be labeled? Are there only two possible outcomes? Right? And finally, is the probability of success on any one trial the same as on any other trial? Right? If you can answer yes to all of those, then it's a binomial experiment. There are four symbols that always mean the same thing in the context of a binomial experiment. N, lowercase n, always means the number of trials. Right? You have to know these because they're used without comment in problems and so on. Right? N means the number of trials whenever you're talking about a binomial experiment. P, lowercase p, is the probability of success. Q is 1 minus p, that is, it's the probability of failure. Right? Because failure and success are the only possible outcomes for a trial, their probabilities have to add to 1. So Q, the probability of failure, just has to be 1 minus P. And finally, capital letter X, this is a random variable that counts the number of successes. Of course, it means in the n trials of the experiment. So you think of a binomial experiment as being a big experiment made up of little experiments, and the little experiments have to follow these rules, and then these variables are used to talk about the experiment, the little experiments and the big experiment as a whole. The thing we're interested in here is the number of successes. Right? You perform the n trials, you want to count how many successes happened, or rather, what we're interested in is what's the probability that there were no successes, or that there was one success, or two successes, or whatever. That's what we'll be interested in. Okay. So let's look at a couple of examples of this. Here's the first one. An experiment consists of flipping one fair coin one time. Success is defined as getting heads. What are all the possible outcomes? What are N, P, and Q? And what are all the possible values of X? Okay. What are the possible outcomes? The possible outcomes of one trial, right? The possible outcomes of one trial of the experiment. Well, a trial is just flipping this fair coin, so the possible outcomes are heads and tails. The possible outcomes of the whole experiment, the whole big experiment, is the same because the experiment consists of just that one trial. Okay? What's N? N is the number of trials, so it's just one. What's P? P is the probability of success on any one trial, so here that's 1/2. What's Q? It's just the probability of failure, or 1 minus P, which is also 1/2. And what are the possible values of that random variable X? Well, you could flip the coin and get tails, and then that would be 0 successes, so that's a possible value of X. You could flip the coin and get a head, and that would be 1 success. That's the other possible value of X. So the only possible values of X here are 0 and 1, the only possible numbers of successes. Okay, let's push that just a bit further. An experiment consists of flipping one fair coin twice. Success is defined as getting heads. Find each of the following. So I'm going to stop here and remark that success is defined as getting heads. Success is only defined on each trial. It is not defined for the whole experiment. There's no such thing as the success of a binomial experiment. There's a success of each of the little trials. Right? That can end up in success or failure. But there's no success for the whole thing. There's only counting how many successes there were on the trials. Okay, let's find each of the following. So N, what's N? That's the number of trials. We're flipping a fair coin twice. So we're going to think of this as a binomial experiment in which each of the trials is flipping a coin one time. So there are 2 trials in this case. What's P? That's the probability of success on any one trial. And of course, that's still 1/2. This is a fair coin. Success is getting heads. So P is the probability of ending up with a head when you flip the coin. So that's 1/2. Q, of course, is also 1/2. It's 1 minus P. What are all the possible outcomes of one trial? One trial is flipping a coin, so that's heads and tails. What are all possible values of the experiment, meaning the whole binomial experiment? Well, the experiment is made up of 2 trials, so when you write down an outcome of the experiment, you have to account for what happened on each of those trials. Right? So what could happen? You could get heads on the first flip and heads on the second. You could get heads on the first and tails on the second, or tails then heads, or you could get tails both times. Right? So those are all the possible outcomes of the experiment. What are all the possible values of the random variable X? Well, you could flip the coin the first time and get tails. You could flip it the second time and get tails, and then X would be 0. Since success is getting heads, getting tails both times would mean 0 successes. That's a possible value of X, 0. You could get heads only one of the 2 flips, or you could get heads twice. Right? So these are the possible values of X in this situation. Okay. As I said, what we'll be interested here in this binomial experiment situation, what everybody is interested in is what's the probability that X takes on a particular value. Right? So when we get around to writing a probability distribution for X, what's it going to look like? I won't put any values in just yet, but let's say what it's going to look like. Well, we're going to have a table. Right? I'm going to make it horizontal in this case, And there are going to be the various values that x could take on, 0, 1, 2, 3, however many, right? However many there are, ending at the number of trials. And then we need the probability that x takes on each of these values. So we would be putting a probability in here for the probability of 0 successes, and here for the probability of 1 success, and so on. Okay, so let's actually construct such a thing, a probability distribution, for the case in which, for the binomial experiment in which a fair coin is flipped 5 times and success means get heads. So what do we have here? We have n is equal to 5. P, the probability of success on any one trial, is 1/2 again. And we need a table that looks like this. X, little x, for the number of possible successes. And that's going to have values 0, 1, 2, 3, 4, and 5. Those are the possible values of x. And then the second row here, I'm going to put the probability that the random variable capital X actually has the value little x. Right? So this right here, this will be the probability that capital X is equal to 0, and this the probability capital X equals 1, and so on. All right. The way we get these is to use the calculator. Right? So the probability, in general, the probability that the random variable x equals the value little x is given by binom PDF, the binom PDF function in the TI calculator, which I'll show you in a moment. It takes 3 arguments. It takes n, the number of trials. It takes p, the probability of success on any one trial. And it takes little x, the number of successes you're interested in finding the probability of. So, for example, in the case of this experiment here, the probability that the random variable x is equal to 0 is binom PDF of number of trials is 5, probability of success on any one trial is 0.5, and then I'm interested in the probability of 0 successes. And you'll see how to, we'll just do it. Let's go ahead and just do this. Right. Where is the binom PDF function? See, next to the rocker switches here, you have this vars button, and above that, you probably can't read it from this screen, but I hope you can on your calculator. Oops. Right. There's a DISTR label, and that's the distributions menu. So to get to it, you want to push second vars to get to the distributions menu, and then you want to arrow down, it's quite a long way here, until you come to binom PDF. There's a binom CDF right underneath it, which we'll also use, right? But don't confuse the two. Here we want binom PDF. I'm going to put the highlighting on it and press enter to put it on the screen. And now I need to put in the 3 arguments. Right? The 3 arguments are right, n, which in this case is 5, and then I need a comma, and I actually use the comma key above the 7. 5, comma, now p, 0.5, comma, and then the little x I'm interested in, right? And press enter, and there it is. There's the probability of 0 successes in 5 trials, where the probability of success is 1/2. So I could put that here, 0.03125. And I could fill out the rest of this table in the same way. So let me go ahead and put in the numbers. All right, that's how you get the probability of some particular number of successes. That is to say, binom PDF of n, p, and x, that is the probability of exactly x successes in the n trials with the probability p we had. So there's also this function which you saw a moment ago, binom CDF, that's for cumulative distribution function. The arguments are the same. Right? Number of trials, probability of success on any one trial, the number of successes. But this time, what you get back is the probability of at most x successes. Right? That is the probability that the random variable x is less than or equal to the value little x. Right? We'll see that used in just a moment. Right? But the problem is we also need to find probabilities like this, the probability that the random variable x is greater than or equal to some number. Right? That is the probability of at least x successes. Well, there is no calculator function that does that exactly. Right? So this is the kind of thing you have to do. Now, let me explain what gets done here. It's very easy to carry out, but let me try to explain what gets done. So suppose, for this experiment right here, suppose we were looking for the probability that x is greater than or equal to 3. That is, 3 or more successes. I could compute that, since I have the whole table here, I could compute that by adding these numbers together, right? The probability of 3 successes, 4 successes, and 5 successes, since that's what it means to have x greater than or equal to 3. Another way I could get it would be to add these 3 numbers together and subtract the result from 1. So the probability x is greater than or equal to 3 is 1 minus the probability that x is less than or equal to 2. And that's how you find the probability x is greater than or equal to x on the TI calculator. If you want the probability x is greater than or equal to x, you have to do it like this. 1 minus binomial CDF of n, p, and x minus 1. Just like up here, the probability x is greater than or equal to 3 is 1 minus the probability x is less than or equal to 2, because those are complementary events, right? This event here, 3 or more, is the complement of this event, 2 or fewer. For this particular experiment, well, I won't compute any of that in the case of this particular experiment, because we're going to go on to another example in which I actually will compute it. Okay, here it is. A certain surgery is successful in 80% of cases. Okay, so part A, the surgery is performed 4 times. What's the probability of exactly 2 successes? So this is a binomial experiment, right? It has independent trials. We don't suppose that the outcome of surgery on one patient has anything to do with the outcome of surgery on the other, right? And so we have, let's see, 4 trials, so n equal 4. Probability of success on any one trial is 0.8. Success is very clearly defined here. Sometimes you have to read a problem and decide what success is. Right? And what we want is the probability of exactly 2 successes. That is, we want the probability that that random variable is equal to 2. And we know how to find this. It's going to be binomial PDF, since we're looking for the probability of exactly something, PDF of n, p, and x. So this would be 4, 0.8, 2. And you just put this in your calculator. You'll find out that this is 0.1536. You've already seen that one done. Okay, what's the surgery is performed 60 times. What's the probability of at most 50 successes? Probability at most 50. I want the probability x is less than or equal to 50. And for that I'm going to use binomial CDF NPX. Right? So number of trials, there are 60 trials this time. P is still 0.8. And the probability of at most 50 successes means I need to put 50 in there. And so we'll actually do this. We'll go to second pairs to get the distributions menu, arrow all the way down to binomial CDF, making sure to get the right one. And this time I have 60, 0.8, 50. The probability is about 0.7868, something like that. So about 0.7868. There's almost a 79% chance of at least 50 successes. All right, third part here. The surgery is performed 40 times. So here we have n equal 40. We still have p equal 0.8. Okay, what's the probability of at least 32 successes? That is, we want the probability that x is greater than or equal to 32. Again, there is no button that will get this for you, no function in the calculator that will get this for you. So you have to do it like this. It's going to be 1 minus binom CDF, C, not P, of n, P, and x. And this time n is 40, P is still 0.8, but I have to put x minus 1 in here. If I want the probability x is greater than or equal to 32, I need a 31 right there. And I'm going to do that one on the calculator too, mostly so that you can see that this whole calculation can be carried out at one time if you want to. I'm going to start with 1 minus. That's fine to just put 1 minus. Now I'm going to find that binom CDF function, second distributions. Okay. I go down until, gosh, I can't see my own screen. Binom CDF, and press enter to put it on the screen. And now I want to put in the three numbers, right? 40, 0.8, and 31. So 40, comma, 0.8, comma, and 31. Okay. And Bob's my uncle. It's about 0.5931. Okay. It's about 0.5931. Okay. Let me just say one more thing very briefly. This is not something we're going to use right away, but it's kind of a natural place to put it. Right? It's about the mean and standard deviation. That's supposed to be an ampersand. The mean and standard deviation of a binomial distribution. Right? That's what I want to talk about. And I'm just going to give you formulas for them. The mean, right, or expected value of that binomial variable x is n times p, where n is the number of trials and p is the probability of success on any one trial. That's the mean. Right? The standard deviation is the square root of n times p times q. Right? That's the number of trials times the probability of success on any one trial times the probability of failure on any one trial. You remember that q is just 1 minus p. Right? Okay, as I said, we won't use these right away. We'll use them a little later, but this is kind of a natural place to put them. Okay, that's about it for this lecture.